The problem I'm talking about has been introduced in the two previous talks already, so it's the ST path traveling salesman problem. Before I get into it, let me give an overview of the state of the art of the TSP and some variants. So the standard TSP you can see here. I always show the lower bounds on the integrality ratio of the standard LP and the upper bound on the integrality ratio, which is in most cases identical to the best approximation ratio that we have, but in some cases for ATSP there are some differences. So you don't have to look at all the numbers. What I want to show is there has been a lot of progress during the last 5 years, after long silence, I would say. But there are still, essentially all questions are still open. Yeah? So I think we should still make more progress during this trimester. So today I will talk about the ST path TSP for general weights, and I will show how to improve on the previously best known approximation ratio 8/5, which is due to Andras Sebős. So the problem is very easy to describe. You are given a set of cities with distances. You have two specific cities, S and T. You want to start at S and at T, and in between visit all cities. And you would like to minimize the total distance traveled. You can visit cities several times, that's fine. But an equivalent description, as was just proved in the previous talk, is that you indeed visit every city exactly once, but then you will need to require that your distance function satisfies the triangle inequality. So that's the version I will work with here. We have a finite set of cities, S and T, origin and destination, and a metric on these cities. So we're looking for an ordering of the cities. S must come first, T comes last, and we minimize simply the total distance, right? So it's a very simple problem. If S is equal to T, that's the standard TSP. So the two approximations, this double tree algorithm as in standard TSP works, so that's very easy. Christofides algorithm works as well. The only difference is that for S and T, you need now odd parity, and for all other vertices, you need even parity. That's the only difference. Otherwise, the algorithm works as everybody knows it. But it is only a 5/3 approximation algorithm for the ST path case. There are examples where it is no better than this. The first improvement on Christofides algorithm for any problem with general weights, in particular for this problem, was due to, it's not completely focused, due to Ann, Kleinberg, and Schmois, two of which are here. It's by the algorithm that is was called the best of many Christofides. I will explain it in a minute. And this same algorithm is actually better than this ratio, this golden ratio that Ann, Kleinberg, and Schmois could prove. Andras showed how to prove a ratio of 8/5 for this same algorithm. Today we will improve on this ratio, but we will also have to change the algorithm slightly. Good. The first step in this algorithm is to solve an LP, namely the standard LP relaxation. Often it's called the held-cup relaxation for this problem. So it's very similar to the normal subtour LP for TSP. We have a decision variable x, e for every edge, whether or not it is included in our ST path. So we look for a Hamiltonian ST path. Of course, S and T must have degree 1, or the other vertices must have degree 2. And for every cut, we need at least one edge because it should be connected. And in fact, for every cut that does not separate S and T, we need at least 2 edges. So if I would require integrality in addition here, it would be exactly in description of the ST path TSP. But I don't require integrality because then I cannot solve it. And here you find, for example, a feasible solution to this LP in a certain instance. You can easily check that this is feasible. This LP has exponentially many constraints, but you can easily solve it in polynomial time, either by the ellipsoid method or by an extended formulation, so that's well known. Good. So in the standard TSP, you would have for every cut that the value must be at least 2, because you have to go back and forth. Here, this is not the case. Here, some cuts require value only 1, namely the ST cuts. And if you look now at all cuts that have indeed value less than 2, in this example, these are these red cuts here, then they happen to form a chain, and that's not by accident. This is always the case, and that was already observed by Kleinberg and Schmutz. So in the following, I call these the narrow cuts, the cuts where we have value strictly less than 2, and they form a chain. This we should keep in mind, because they will require special attention. So here is the description of the best of many Christofides. The first step is just solve this LP. Let's X star in the following denote an optimum solution to the LP. Then the second step is we decompose X star into spanning trees. So we write it as convex combination of incidence vectors of spanning trees. It's easy to see that X star is in the spanning tree polytope. The spanning tree polytope contains the feasible set that we just had. And there are several methods how you can write this as convex combination, by ellipsoid method or by splitting off. Andras Frank didn't know this, maybe, but in this Genova of Williamson paper, they describe how to do it by splitting off, essentially using results from your book, which, by the way, you can find in the coffee room, but not take it away. So we do this, then we have a couple of spanning trees. Actually, we can assume that we have less than n square spanning trees that have really positive coefficient. And for each of those, we do parity correction just as Christofides does. So we just find a minimum weight perfect matching of the vertices that have wrong degree, or equivalently at a minimum cost TS joint. So TS will always denote the set of vertices whose degree is wrong. That means whose degree is even if it is S or T and odd otherwise. And then we take the best of these. Well, this is, you may say this is not a tour, but this requires all, is connected and requires all the parity constraints, and by the usual shortcutting argument, you get a Hamiltonian ST part that is no more expensive than this. Good. So that's the algorithm. The best of many Christofides, and we will slightly modify it in a few minutes. So let's see how the basic analysis of this algorithm work, and that's all due to Kleinberg and Schmutz. So the cost of the solution is the minimum of all trees that contribute to our convex combination. We have the cost of the tree plus the cost of parity correction, right? And the minimum is clearly less or equal to the weighted average. That's evident. And now we have two summands here. So if we take the weighted average of the first of the trees, that's exactly C of X star, because we decomposed X star into the trees. So what remains, so that's easy to analyze. I mean, C of X star was a feasible, an optimal solution to our LP, so certainly a lower bound on the optimum value. So we have already 1 times opt, in a sense. All the rest is about to bound the rest. So here we have the convex combination of the parity correction costs, which are a bit more difficult to analyze. The first important idea is that instead of bounding this, we could take any vector ys that is in the T-joint polyhedron, or TS-joint polyhedron. So here's the standard, I mean, the well-known description of the T-joint polyhedron. And we know that for any cost vector, the minimum cost of a vector in this set equals, for any non-negative cost vector, the minimum cost of vector in the set equals the minimum cost of the T-joint. So if I take just any vector ys in this set, it's certainly an upper bound. So we call these ys vectors correction vectors in the following, because somehow they bound the cost of parity correction. And once again, I can take any vectors ys for all these trees that I need that are in this polyhedron. Good. The next step, so how to choose these correction vectors. Oh, maybe before I should make one remark. So as ys, we could, for example, take x star, because x star has certainly this property that we have x star of c for every cut is at least 1. I mean, that was one property, the connectivity property. In the standard TSP, actually, we even have at least 2. So x star over 2 would be a feasible correction vector, and that's exactly Lorenz's analysis of Christofides' algorithm that gives the 3/2 upper bound on the integrality ratio of the sub 2 LP in the normal case. But here it's not the case. Here we cannot use x star over 2. We still use x star to some extent with some factor beta, but not with beta 1/2, with a smaller number of beta. Then the next step is that we, for every tree, it partitions obviously into an ST path, or the unique ST path in that tree, and the rest. And the rest is a TS join, which is very easy to see. So I denote always in every tree by blue and by IS the unique ST path in the tree S, and by JS the rest, which is a TS join, so that the incidence vector of JS is also a parity correction vector for the tree S. So I will use this also, and this is not new, as mentioned. So this, I will use this also to some extent with some factor here. So beta will be roughly a bit more than 0.4 in the end, so to give you an idea. Okay, we have these two components. But this is not sufficient. So we need some remaining part to correct for what is not yet good. Namely, for every cut we need at least 1, and that means, so we have 1 minus 2 b. I mean, this is for every cut that we need to correct, we have at least one edge. So we have at least 1 minus 2 beta plus beta x star. So this is exactly what is still missing. Oh, this is at least not more is missing. So with RS, we need to cover this amount here. If we have this, if we can choose vectors RS with this property, then we are fine. Then we are in the TS joint polyhedron, and then the rest works. The only question is how to choose this. Of course, it should be still cheap, these vectors RS. Okay. Now, this is just nothing new. This is just what was on the previous slide. So we need this property here. Andras' idea was, now, okay, we have this x star. We know x star is, yeah, the cost of x star is the optimum, or at most the cost of the optimum. Now we have this JS here, which is part of the trees. Well, we can, if we can bound the cost of the RS by, actually the C is missing here, by the cost of the blue parts of the spanning tree, then the blue and the red together make all the spanning trees, and so together they make again x star, so that would give an easy analysis. So if we can bound the weighted sum of the RS vectors by a weighted sum of the incidence vectors of the blue parts, in this sense, exactly by 1 minus 2 beta times this weighted sum, then what we really have, we have beta times x star plus 1 minus 2 beta times, well, the convex combination of all trees, red and blue, which altogether is also x star. So we have 1 minus beta x star is the total cost for parity correction. Of course, we in addition have to pay for the trees. So say if beta is 2/5, then we have here 3/5 for the parity correction cost plus 1. So we have the 8/5 approximation ratio that Andras could prove. Okay. Now we want to improve on this. So once again, here is our spanning tree with red and blue part. So we want to bound what we have in RS by the total cost of these ST paths that we have in all the trees. So let's look at one tree and at one specific edge, one blue edge, so one edge in the ST path of that tree. Then what we have is 1 minus 2 beta times the coefficient of that tree. this we can distribute somehow to the R vectors. That's the amount that we have. And Andras proposed to do it in the following way. To give half of this amount that we could spend, that we have for this HE, to the same tree S, to the same correction vector RS. That somehow would help because it will correct the even cuts in that, the even narrow cuts in that tree. So in this case here we have the narrow cuts shown by vertical lines. Some are even, they need parity correction. They are shown here in bold lines, and the dashed ones are odd, so they don't require parity correction for this tree. So Anders said, well, let's do half of it, go to the tree itself, and the other half we can use for other trees. And how will we use it for other trees? So there can be at most one cut, one narrow cut, in which E is the only edge of that tree. I mean, if there were two, it would simply not be connected. So, so since spanning trees are connected, there can be at most one such edge. And so I will put the other amount that I still have, the other half, into a box that is assigned to this cut, where this is the only edge. And then the other trees can take out of this box if they still need something, if it's not already done. And that works out. I mean, the idea is, I mean, we need, if we go back, we need beta times this amount. So if x2 is pretty close to 2, we need very little. If x2 is close to 1, if x star is close to 1 for the cut, we need quite a lot. So then this may be not enough what we get here from the edges themselves. But if it's close to 1, then we will have many trees where there's only one edge crossing the cut. So we will have many contributions of the second kind. So we will have enough in the box. That's the intuition. And if you do the calculation, you get that it works for beta equals 2/5, and therefore get 8/5 approximation. So now I propose the following change. Instead of doing it half-half, why shouldn't we adapt the ratios according to criticality? I mean, some cuts may be really more critical, and the critical case in the previous analysis was exactly for the cuts with value 3/2. That was the worst case. If there were no cuts with value 3/2, you got immediately an improvement. So let's call the cuts with value 3/2 the most critical ones, because for these the analysis was really tight. So suppose this is a really critical cut, this one, and the other two that are crossed by E are not so critical, then I would actually put more, like to put more in the box and spend less for the tree S itself. And the other way around. If one of these two is very critical, but this is not, I would do it the other way around. So it's very natural to adapt this. And by this you can improve, unless, I mean, there is of course a problem. So we distribute this according to criticality. I don't give you the exact formulas here. The problem is if such an edge is is in two critical cuts, one of which is even, and in the other one it is the only edge. So for example, if this cut is critical, has value 3/2, say, and this also, well, then we don't know what to do. And if for some cuts, some narrow cut, all trees have this property that you don't know what to do, then you will not get an improvement from this. So we need to be a bit more careful about this. So in the following, I will ignore, I said narrow cuts are those with value less than 2, but I said already that those with value around 1.5 are really the ones that prevent us from improving. So I will now ignore the cuts with value more than 1.73. That turns out to be a good number. The precise number is not so important, of course. Now let's look at situations that can happen at a narrow cut. So here C is a specific narrow cut that I'm now analyzing. And let C left and C right be the next, no, they form a chain that we know the narrow cuts. Let these be the next narrow cuts, the real narrow cuts. I mean, those with value less than 1.73 to the left and to the right. Then in each row, I show certain configuration that a tree can have at this cut. So I show the intersection of a tree with this cut. So for example, it could be only one edge, like here, that does not extend is not contained in the previous and not contained in the next. So it's only contained in this narrow cut among those three. Then it's actually easy because we can put more in the box, right? This is the only edge in this narrow cut, so we don't need anything for the tree itself, or at least not as much. So we can put more in the box and we get an improvement. Here the same, the edge in the tree does not extend to any of the other cuts. Well, there are two, I will then spend more for the tree itself. I don't need anything in the box here. So these green cases are very easy to deal with. Then we have let's look at the blue cases next. So here we have only one edge, but it extends to both sides here, to both the next narrow cut left and right. Here we have two edges, and both the one in the ST path and the other edge extend to the next one, and so on. Well, now the next observation is that, so for the green ones we can improve immediately. For the blue ones, they cannot happen too often, because the intersection of two narrow cuts cannot be so big. I mean, I may have time for this. So if you look at x star of C, let's say C left intersection C, if you take x of C left, no, I should only be consistent, the same works for right, of course, and x of C, well, and I subtract x of delta of S, where S is the set in between C left and C, so this is the set S in between, then I count everything, except that I count what remains is exactly the edges here, but I count them twice, so I have to put 1/2 here. Then this gives the exact formula. And so this here, we know is at least 2 because it's a set that does not separate S and T. Now this is at most 1.73. And this also. And if you sum it up, you get that the total value is at most 0.73. So that shows that cannot happen. I mean, only 73% of the trees can have an edge that is both in the C left and C. And the same, of course, for C and C right. So since we have two such edges here, that cannot happen so often. That can certainly not happen for all the trees. So that's the observation. So what remains, I mean, there are some cases that remain that are even less critical when we have 3 edges or more. What remains are the red and orange cases. They are indeed difficult because we have only one edge that extends, and yeah, the edge in the tree also is in 2 critical cuts. So these are problematic cases. So these I would like to get rid of. I don't know how to get rid of them completely, but what I can do is I can get rid of one of the 2 red cases completely. I can also get rid of one of the 2 orange cases completely. And I can essentially get both. Essentially, I mean, I don't make this precise. This is what essentially now. And that turns out to be sufficient. I mean, then you have to look at 4 cases that remain, and it turns out to be sufficient to get the improvement. So how we get rid of these cases, and that's the reassembling trees. Now that it was in the title, that finally comes up. So we add an extra step in the algorithm. So we solve the LP, we decompose it into spanning trees as before, but then we will change this distribution to spanning trees to avoid these combinations. So look at, here is a bad combination. Here are 2 trees, and at this narrow cut, well, this is one of the bad cases. Let's see, this is I call it 0, 1, 1 here. I mean, 0 edge, 1 edge, 1 edge, yeah. It was the notation here. So this orange case, and now we have the other orange case, and suppose they both occur simultaneously. Here's the other orange case. We have two edges in our tree, and like this, and here we have one edge in S2. And what I simply do is, if I have such a situation, I will swap two edges. So I will simply take out E1 here and take out E2 here and add it to the other tree. Of course, you have to be very careful when you do this. For example, you should still have trees afterwards. But if you do it in exactly this way, if you take the short edge here, that is, and if you take the only edge in the cut here, you can prove that the resulting graphs that you get are still trees. Moreover, they are now good because this is a blue case and this is a green case, so we have improved. We have avoided these cases. And now, of course, you have to iterate this and do this as long as you have bad cases, essentially. And if you are careful enough, you get what is needed. So that gives the intuition. The details are, of course, a bit involved, more involved than I can do in 30 minutes. Instead of giving the details, I would like to conclude with some remarks and open problems. So if I do all these calculations, what I get is an approximation ratio better than 1.6. That was clear to me relatively early, but to do the actual multiplication was not so easy. So I got 1.599 with reasonable effort. With even more effort, I could probably get to 1.598 or something. But it gets more and more complicated. So, yeah, as I said, I think I can get 1 point. I mean, I stopped here because we can get an improvement, but the improvement is small, right? And it doesn't matter so much whether 1.598 or 1.599, I would say. But I will not get to 1.59, for example, with this technique. That I know. Yeah. We get the same bound on the integrality ratio, so 1.6 is not the true answer that we know. I mean, we guess that it's 1.5, like in the unweighted case, but we cannot prove this, and this alone will not be sufficient to prove it. So we either need stronger reassembling results. I mean, I just looked at these bad cases that prevented me from getting an improvement immediately. Maybe I also can think about start with not an arbitrary distribution, but I don't know, max entropy distribution has proved useful in some cases, or something. Try, I don't know, there are many things. There's this swap round is very similar that has been proved successfully. I don't know how to analyze this. A very natural question is, I mean, this was for ST path. I mean, the previous algorithms worked for T tours, where T specifies which vertices must have odd degree, and all the others even degree. So if T has exactly two elements, this is ST path. If the previous algorithm worked with the same analysis for larger T, here I'm not so sure. The narrow cuts don't form a chain anymore. There are some differences, and it may still work, but I'm not sure whether it does. And of course, most interesting, can we apply a similar technique to other TSP variants? I mean, many of these work with these convex combination of trees. Can we do similar things for other variants? That would be, of course, the most interesting question. Thank you. I don't think so it would, but yeah, in some cases actually for this extra, what I said, when going from 1.599 to 1.598, we actually look at more cuts, but it gets more and more complicated, and then you have to solve an integral, and then it gets ugly, and so I'm not sure whether it's worthwhile.
I guess I have one question similar in the sense that, so you start by taking an arbitrary decomposition and then repair it. But is there a way of sort of doing the splitting off? I mean, if you go back to the Genova-Williamson, perhaps there's a nicer characterization of what kinds of trees are okay that you could still guarantee by
not seriously. I mean, I don't know how to. It would be certainly very interesting. I mean, certainly the distribution that I get is not the best. I mean, that you need to do something about the distribution. The example that I showed in the beginning actually shows that otherwise, at least with the framework that we have, you cannot improve beyond 1.6. But certainly the operations I showed will not yield the best distribution or in any way.
Can you remind us what is known for T2s or larger T?
We have 1.6. Andrasch works for any T.
Okay, thank you very much.